Hello everyone. Today we have the second last part of Franz talk about dispersion.
So, thank you for your introduction. Let me first have two remarks, two questions from last time. The first one was the flux. Remember, you had the vector density and integrated it over a two surface. Yes. E to x and a e AI. So, and it wasn't so clear what this means. This is a normal one form. This n over this n a e to x. And you can write, I can write it n a e to x. Okay. Well, NA, oops. NA is normal one form. We can write it as a vector product on the surface. And we have NA into x, so this is a two form. Epsilon A E C dx dxc or is dx2 component A. So here we have a two form, it's just the Hodge dual of this one form, and then we can write E I integral E AI epsilon ABC EXE DXC. Now we have an integral over a two form. Well, but E was the form E I is C DXE DXC. Well, this EI is just, this is the two form component. So we can see it as a integral. The flux is can be formulated as a integral over two form. So this is, here we have a vector density, and so here we can find an invariant integration over a two form. So the first remark. The second one concerns Lorentz invariance. Well, of course, when we have a canonical formulation, general relativity, so that first cycle and beginning, the first principles, Lorentz covariance cannot be a principle because not only a space like hypersurfaces, and then we cannot carry out Lorentz transformations. But this is the same whether we have ADM formalism or the formulation of multiple variables. But in classical theory, local Lorentz invariance can be restored dynamically. So when we have constructed hypersurfaces, on each hypersurface, we have the constraints we have in ADM formalism. We have the Hamiltonian and the diffeomorphism constraint. In the Ashtika variables, we have, in addition, the Gauss constraint describing or generating SO3 rotations on each spatial hypersurface. And when we have constructed such a four-dimensional manifold by constructing further hypersurfaces, then we can here choose coordinates, orthogonal coordinates, and how to, and what we can transform with the aid of the Hamiltonian constraint. We can slightly locally deform, like this, a hypersurface. That's too much. So when we insert some special tangent vector here into the Hamiltonian constraint, we can somehow deform these hypersurfaces. And this one can be also deformed or shifted by the diffeomorphism constraint. So this is a normal vector. And then when we take here, when we here insert, say, in the simplest case, just one coordinate vector, say x, then we get here a deformation in that direction of x. And here we take the diffeomorphism or the x component of the diffeomorphism constraint in a dependent way from each other. Then we can locally have new coordinates, or the space-like coordinates, and the time-like, or space-like vector, and time-like vector, and this can be arranged in such a way we get just a Lorentz transformation locally. We can do it at every point, but of course there's no global Lorentz or Poincare invariance of Earth space-time. And as I've already said, you can do it from the canonical general relativity in Ashtika variance. So in addition, you have the rotations here, spatial rotations, so you get the full this autochronous Lorentz flow locally. And but in quantum theory, that's a problem. That's another question, and this is not so sure. So I think beginning from the 80s, the 90s, and after 2000, there was a whole industry of formalisms in some way violating Lorentz invariance, like double special relativity, which is double in the sense that special relativity is special, but it has an invariant speed of light. And double special relativity has a further invariant quantity. And in most cases, the maximal energy and momentum of a particle. And this can be quite easily done, but if you have such an easy, simple formalism, then you have to decide whether something is an elemental particle or not, or some maybe a microscopic body. This led to the infamous soccer ball problem, how to describe microscopic bodies in this formalism, or mathematically more sophisticated double algebras, bi-algebras, or Hopf algebras in momentum space and in space-time, or relative locality, so-called rainbow matrices, so that the metric should depend on the energy of an observer, and so on. And I think there's not a final solution to this problem. Can Lorentz invariance be some place be violated or not? As far as also in string theory, there are similar considerations. about non-relativistic behavior of high energies.
No,
And this,
no, I don't think so.
no, not
I mean,
anymore.
string theory norms is a small part of it.
So, what's our Java bitten? Not sure anymore.
There's no violation in general.
Anyways, this was one motivation for this work, to see how do gravitational waves behave, or if you add electromagnetic waves, either dispersion or not. So, and to continue from last time, we had quantum states. One-dimensional spin networks, or sometimes called charge networks, this was effectively the case through U1, and we had point prolongments. Parentheses. We know M, P to Y, and okay. And then obviously, and then the full point prolongment around the tensor product. And then we have H prolongment. By K, E to I and K, and the connecting component in the direction of Z of this edges, the Z direction. Then operators, Kx, raising and lowering operator when it acts on Mn, we get 1 over I, n plus 1 m minus m minus 1 m ky. Obviously acting on n, and k on k is 1 over I, k plus 1 minus k minus 1. But we don't need this. And then the flux variables, Ex, when it acts on m, is just a factor of m. It just differentiates with respect to k, so it gives it gives the factor m, 1 times I times the band length, Ey, and it's n, and E, k is k. Yeah, then the killing conditions. I've written down once more. And then dispersion-free propagation of waves with exactly the speed of light was formulated in form of killing conditions, or the existence of killing vectors, non-killing vectors in this or this direction. In terms of these variables, they are here. This describes here we have the z derivative of E, and this is in fact the time derivative, and E is an eigenvalue of the transversal of the transversal cross section. A so-called background factor in the theory of gravitational waves. And this is called the wave factor, giving the difference, or here the ratio between the metric in the x and the y direction. So how a ring of particles would be deformed when the wave goes through. And again, here, space derivative, and here we have time derivative. These are the classical Hilling conditions. Now, in quantum theory, I think here we started last time. Yeah, U plus and minus contain only the connection variables kx and ky, no a, so it acts on edges, on the edge functions, just by multiplication. There's no non-trivial action that it will change over level. So we can associate them to, let's say, U plus can certainly be associated to a vertex. Not completely act in some way non-trivially on vertices. No. So we choose a symmetric factor ordering to make symmetric or permission operators. So that P plus becomes the square root of Ex, Kx, and it's more the square root of Ex. The same for Y. Plus E prime. And U minus analogous square root of Ex, Kx, square root of Ex minus square root of Ey, Ay, square root of Ey plus E logarithm Ey by Ex squared. So now we consider the action on the vertex of this one-dimensional spin network. So let's first consider U plus. Here we define E is K plus minus K minus. Here we have the vertex E and the edge level K plus K minus coming from the Z derivative here of E prime. E is when it acts on edge functions, it's the level K, so here it is K plus, here K minus, and here if you have a derivative, it's natural to take the difference. So, and then, yeah, when the action on some function, a vertex function, given by a superposition with coefficient A and N of polynomials N N. Here we have one rating, one lowering, here two. So altogether we can see a different equation. Oh, it's here. So it connects A M plus M minus N plus N minus with M. Well, what can we begin? Begin with the simplest case that E is equal to 0. We have the same echelons left and right. So begin with inserting M equal to 0 So when we so m equal to 0, 1, I think it's 0, I equal to 0. So and e was assumed to be 0, 2. So it doesn't say anything about a 1, 0, minus 1, 0, 0, plus 1, 0, minus 1. You know, doesn't distinguish them, doesn't distinguish. And yeah.
Can I ask you?
Yeah.
Um, I don't remember, do you have some formula for E and K in terms of variables? I don't remember. I mean, they are operated on the point and edge elements, right?
Yeah.
Do they have some specific?
Yeah, here are two questions. The operator K acts as raising and lowering of the representation of the group in one. It raises or lowers the average by 1. And K Y raises and lowers of n K Y. And E just multiplies by the lambdas. These are the eigenvalues of the E operators. Just by differentiating, to differentiate this with respect to Kx, so that I have n with Planck's constant or I, and when I is the immunity parameter, if you don't suppress it, and the Planck is square. So it's a square. It's an area. A value of.
So you express E in terms of the variation with respect to K.
Yes. Relation with respect.
So you're in the connection space. Yeah, in the connection space.
We have a connection representation.
Yeah. Yeah, I mean, you express everything in terms of K and not E.
Yes, yes. Yes, the functions. Yeah, it's leveled. You know, use the holonomies of K. What A? This is a H function. This is an holonomy. Yeah, and applying it in this way, we find this differentiation when we insert 0, then and also for n is n0 or 0 n also in most cases a n 0 a 0 n so we can use an arbitrarily.
Sorry, another question. Is that K the extrinsic curvature or the aspect variable?
It's the extrinsic curvature.
So it means that actually the holonomy there, that A would be the connection with
Yeah, this A.
the normal vector to some
Yeah, this
curves
are
and
just extrinsic curvature. The Poisson brackets and the commutator are the same. Yeah, sure. Yeah. So this model is more convenient. Yes. What's the model using? Yes.
So we are saying that essentially that A in the homotopy
Yeah.
is not the Ashtekar A, but it's just the K minus.
Yes, but in the point column is well, what to go with the case. I just when I do it out from regulations about the value model. I think I had an argument last time why it's better, why it's more convenient. So that it was taken over from a polarized value model, where the Gauss constraint or the rotations around the z-axis are already taken into account, already fixed, and so forth. That's the reason we just don't need the gammas X and Y. It's more convenient just to work with extrinsic gravitational.
Okay, I mean, there is no longer the Gauss constant, right?
No, it's not seen here anymore. It's already fixed.
Yeah, we are the one dimension, so it's.
Originally, you can introduce still a rotation around it and fix it by the Gauss constraint.
Okay, so you said that it is broken, so you can work with the extrinsic curvature. So you don't need the Gauss
We
constant.
don't need it anymore. It's already taken into account. So one can choose, all coefficients. Or n equal to 0, being 0. This means we avoid zero volume states. The volume is the value of Ex, Ey, E. And we can restrict ourselves to one quadrant. And we have initially here m in 0, 1, 2, 3, 4, and 2. We can begin here by 1, 2, 3, 4, 5, and also here. So we have like this, and it's enough. It's the same for all four quadrants. The zeros zero coefficients in a solution are equal to 0. They can be, well, they are in this formalism that a difference equation does not connect them with other ones. So we can settle them simply equal 0. So then, for the case E equal to 0, so that's right hand side here is equal to 0. I calculated 3 exact solutions. You can give initial values at the diagonal. And for example, I can give here 1 somewhere, and here the zeros, and also here zeros. Then I get a symmetric solution with non-zero values here and here. symmetry and non-zero when m plus n is even. This is one possibility. We can also construct all solutions. We get when we take, for example, here one pair of antisymmetric values, initial values, and maybe here also zeros. Then we get here, and so on, non-zero coefficients. This is antisymmetric. M plus n is all. And of course, we can, for every initial value here, we can construct one symmetric solution, and for every pair, plus, minus, one, minus, or whatever, here, we get an antisymmetric solution. And the first one we have here. This comes from A1 is equal to 1, A2 equal to 3, and all equal to 0, and 0, 1, A1, 0, A no zeros. 2, 1, 1, 2, and 2, 3, 3, 2, and 1 are also 0. So I find this solution again. And also calculate it for choosing here an initial value on 1 equal to 0, and the other ones also found for similar formula, and for one antisymmetric pair. I don't have to write them down here. Yeah, this is just a reformulation when P is equal to 1/2 n plus n and Q 1/2 n minus n. Then it looks like that. So after having this one relatively simple example, we look at normalizability. We assume, obviously, n, the scalar product of two basic functions, polynomials, is equal to delta n prime, delta n prime. And then for the solution, one, we find times I is equal to 1 when A11 is equal to 1 plus then the sum p going from 2 to infinity. That's m plus n half. So this is position 2 plus 2 is 4, and all that is 2, and then p goes on here, and q is goes in this direction. For every p, you have a q going from 1 to p minus 1. And so twice, because with an upper half and a lower half, q going from 1 to p minus 1, 8pq square. So, and now we insert this. This number, this sum q going from 1 to p minus 1, you have 4 q square, p square, q square. Now, if we take this apq square divided by p square minus 1 square. This is 4 divided by p square minus 1 square, and then the sum. All it depends only on p, the first part, and this cancelled here. Sum q1 is p minus 1, q squared minus 4, p squared minus 1 squared, and the sum of the q to the fourth. So now we need only the dominant part of this. This is p minus 1 to the third divided by 3 and so on, and lower powers. And here's the highest power is p minus 1 to the fifth divided by 5 plus and so on. That will take the sum over p. For large p, or p much larger than 1. When we here insert p minus 1 to the third, we get p minus 1. Here we get approximately p to the fourth, p squared. And we get this is this is p to the fourth. Here we have p to the third. Here we have p to the sixth, p to the fifth. So this is also like 1 over p, the dominant terms, plus lower powers. So for large p, the sum q going from 1 to p minus 1 goes to 8 over 15, 1 over p. So we have that up. Sum over p is converted logarithmically. So we could, or one possible conclusion could be, we could finish it, we would say, well, it's not possible to satisfy the given conditions. So there must be some kind of dispersion, else this wouldn't work. But we still continue still a while. We haven't yet considered U minus.
Is it possible to renormalize it?
Yes, we can try to renormalize it in one or the other way. U minus, that's here. So on the right hand side, we have this it contains, here we go. It contains the derivative of the logarithm of the ratio ey by ex. If we take this vertex. The first part, kx ex and ky ey act on the vertex, and then we have a derivative of functions at the vertex. So how do we interpret and ey divided by x prime? So we can take other values here, left and right, and take the which ones. Let's denote it by pi, and we pi plus 1, and we pi minus 1. So as a first possibility, we take a symmetric difference. Derivative of the logarithms. The difference e y, well, then maybe I should immediately insert that the eigenvalues when it acts on some polarities, we get n I plus 1 divided logarithm n I plus 1 divided by m I plus 1 minus n I minus 1 and I minus 1. Maybe that's the most natural way. Or we could also define it as a difference here between these two vertex levels, or here, left or right. And then ey divided by x prime, ln and I divided by m I minus ln and I minus 1 divided by m I minus 1, or ln m plus 1 m I plus 1 minus ln m I, or even one should take this difference completely to the left or completely to the right. It seems already rather unnecessary. This leads to simple equations because it doesn't contain m or mi at this vertex. This makes the difference equation simpler. Here, the difference equation is not so simple. But it's maybe more convenient when you want to calculate. To go from vertex to vertex, going to the right and to the left, so we can go. With this, we could go from left to right, here from right to left. But it's more complicated. And in the original paper about the Gaudi model, I found a version by taking the difference on such an interval or such an interval. But on the other hand, there is no vertex variables, and so the derivative somehow collapses to the value here, which seems to me quite unnatural. I did in the same paper. The second derivative, somewhere appearing in the Hamiltonian constraint, collapses to a first derivative. So I didn't consider this here. Oh, number one. And I do not appear in this logarithm. Thanks to this, u plus and u minus convolute. But this this b is just the difference between the h levels here. There's no e, no m or n, and here's this w from wave factor also doesn't contain it. There's only the neighboring vertex levels. They commute, and so they have a common solution. But it's not so convenient for calculating more here along all the axes. And in two, they appear u plus u minus do not commute. There's no complete common solution. What's possible? One can choose such initial values, but this and this are common. This is possible to arrange initial values in such a way that this would be common. Plus u minus and here the solution is depart from each other. It's not possible to find a complete common solution. So one could disregard it immediately. This is possibility, but I wouldn't do it. I think this doesn't disqualify the possibility completely. We'll see later why. Well, because here this is possible to find common coefficients. Anyway, we'll see. Anyway, here there are problems. Yeah, and in this case, we choose W is 1/2 A plus A1. We take here the average value of the edge levels to the left and right. Well, this logarithm n I plus 1 n I plus 1 minus logarithm n I minus 1 n I minus 1. No. Define it, and does not depend, does not contain ni and ni. So it can be kind of like a constant. W comes from wave factors. We need from that factor. So now we have these two different equations with B and W simple numbers coming from outside, from the side of the vertex. Yeah, common solution. So it's to be for the page of the choice. One. Here it's more convenient to take the sum of the difference of these two operators. Second separates. You can take 1/2 u plus u minus. One and sum over n equal 1 to infinity alpha and only the n, the k plus. Of course, there's only k plus when you take the sum. This subtracts and 1/2 u plus minus u minus acting on n equal to from 1 to infinity beta and following n is equal to 0 instead of u plus u minus, and then this gives the different equations n plus 1 alpha n plus 1 minus n minus 1 alpha n minus 1 is equal to y b 1 w alpha m, and the same for n. I will have theta n plus 1 minus n minus 1 theta n minus 1 is equal to y b minus w beta n. Now the first view of use of coefficients. Well, I chose alpha 1 is beta 1 equal to 1 as initial values, and then we find alpha 2 is y b plus w divided by the square root of 2. Alpha 3 is 1 over the square root of 3. 1 minus 1/2 b plus w squared alpha 4 E plus W third 2 minus 1/2 E plus W square and so on. The polynomials in alphas are polynomials in P plus W. First order, second order, third order, and so on. And the betas, when we go from alpha to beta, we have to replace E plus W by E minus W. And and M is alpha N, beta N. I don't have a full solution like here.
So, sorry, Franz, how did you obtain the alpha set? I got lost there. How did you obtain the alpha set?
Oh, I said from the beginning that alpha, the A and N is a product and separated or added and subtracted these two equations.
Okay.
Should separate this.
Okay.
We put them together. Again, let's have a look at normalizability with very low expectations or expectations already. So let's consider the asymptotic behavior. So we can make from these differential equations, assume that alpha or beta are differentiable functions of m or n respectively, and write a derivative instead of the difference. The first one we get square root of n derivative square root of m alpha m is equal to pi e plus w alpha n. And analogically for the betas. Once again, simply to solve alpha for the major goes to for large n goes to 1 over the square root of m e to I e plus w logarithm m. So again, just only 1 over the square root as before. No. Beta n goes for large n to 1 over the square root of n e to I e minus w ln n. So a and n, I think, I wrote it before, either as this form. And in the simplest case, when b and w are equal to 0, what this means when the levels, when we take the x functions left and right with the same level and also the same vertex functions, well, not the same, but with the same weight factor logarithm n divided by n. Then p and w are equal to 0, and which simplifies to just 1 over n. And that's again not normalizable. And take the sum over m in n over 1 over n. It diverges again logarithmically. Maybe that's not a big surprise. What we did in solving these conditions was, or what we got are solutions with exactly where the outcome is exactly zero without any uncertainty of the Killing condition. This means we have exactly the speed of light, no dispersion. And so it may be a quantum, coming from a quantum principle that when, well, so here already with normalizability, something happens. So it's, well, these are not physically acceptable states. Could be.
So what's the way out?
What?
What's the way out?
The way out. Different ways of renormalization. What I'm saying, it's not possible. There must be some dispersion. What we can, in the end, it will come out, but so we can continue on with renormalizing. So, our holonomies are effectively U1 operators or U1 elements in different representations. U1 M and also K. So, but this appears here in this symmetry reduced model. This symmetry in X and Y simplifies, and effectively we get U1. Generally, in loop quantum gravity, the gauge group is SU2 and the holonomies are SU2 elements. So here we have a basis where we can, so we said that fails just in different U1 holonomies in different representations to form a basis. Yeah, with the, not with the M and N being on. Now the one half of V1, 2, 3, 4. Here, basis states, and also the operators are constructed from it, are matrix elements. J of an element G of SU2, maybe. Matrix elements of SU2 in the representation J. We can provide a basis for states, for state functions, and also they also act as connection points to multiply state functions by such matrix elements. So now that's an inner product.
You're now saying about the loop, the full loop quantum gravity, right?
Yeah, that's full loop quantum gravity for 3 + 4 dimensions.
But okay, in the full quantum gravity, you have the spin network space is given by the tensor product between all the deeper matrices and the interplanets. With interplanets, right? So there is some contraction between.
Yes, there are contractions, but I consider it just the holonomies.
Yeah, but in that case, SU2 is. You have the tensor product, so actually you have an ordering difference. Okay, but now you are in U1. Eh?
Yes.
So the wave function shouldn't be trivial.
Yeah, we have representations of U1. Here we have representations J of SU2. What the effect so far? Okay, the basis of one of these state functions coming from being functions or functionals of the connection. On the inner product, we by the Baker-White theorem. E J of an element G, A, B, E J prime of an element G, say C, E, is one of the dimensional representation, J of 1, integral over SU2, D prime J, G, A, B, E, J prime, G, C, E, and the Haar measure G on SU2. And this is equal to 1 over 2J plus 1 delta J, J prime, delta AC, delta BD. Well, now the renormalization now is that I just follow this inner product to our case. It's a simplified model. It's some alien element, it's a jump, or like renormalization in general. It's just changing something, changing some of the rules and introducing something different. So here,
Well, I mean, normalization is a bit more than just changing something, right? So,
I would follow this, so we could use this from full loop quantum gravity.
right, but I wouldn't say it's the same as renormalization in quantum field theory.
No, it's not the same. No, I don't claim this is not the same. It's just a talk, more or less a talk. Well, with a justification that it might be more correct because in original loop quantum gravity we have this gauge group and this inner product, and it has something here in the denominator, so it might work better. That's all. So that is, yeah, then an n prime is then delta m n prime, delta n prime divided by 2m plus 1 to n plus 1. And this saves at least normalizability.
So you're promoting your theory from U1 to SU2.
Well, I introduce part of SU2
Okay.
into this. Well, into the formalism as far as we have it now.
But your operators are still U1.
Yes, yes. I just borrowed different kind of thing. Yeah, now we see when we take the simple. The simple state, 1 over A and n is 1 over the square root of n. Then we have a sum and n, then we have 2n plus 1, 2n plus 1. And and R, A, and N squared. No, this. Well, so we get 1 over n, 2n plus 1, 2n plus 1, going for large n to 4n squared, n squared. Which now is normalizable. Now we can take the sum, which doesn't diverge anymore. So normalizability would be saved. In this case, of course, it is true because this doesn't appear in the sum because it's complex conjugate, so it's cancels. That's this important factor. And with this additional factor taken from SU2, it becomes normalizable.
Do you know what is the result of the sum? I mean, if you sum
Well, sum over m squared n squared is something with well, it's easy to estimate to find integrals.
okay, yeah.
But the sum is some of the which are I don't know.
What does M and N have to do with the representation of SU2?
They are here in the boundaries are e to I half n ax or e to I half n ax representations of U1.
So you're saying U1, higher U1 charge is related to a higher SU2 representation? Is that
To a higher U1 representation. I just take for a representation M here, compare it with a representation M of SU2. Just in the inner product, just take over the inner product.
yeah, but I missed the link between the U1 representation and the SU2 representations. So is it somehow
Of the representation. If you have M here, so I take M.
yeah, but that's you're saying just I have a J, I have an M, they are both integers, I can take them in the same way. But there must be something deeper for you to say that.
Well, the argument is that originally it should be SU2.
Yeah, but how does the charge in U1 connect with the representation of SU2? Right, the N is somehow a U1 charge.
Yeah, I just introduced it ad hoc. What should I do if it diverges?
No, I thought you could make some stronger kind of argument saying that, well, inside SU2, I can sort of fit some U1 subgroup that I'm looking at, and then the representation of the SU2 is somehow related to that subgroup.
This could be done, yeah. So far, just say, well, here we have a certain representation. I take the corresponding inner product, which would come from SU2 in the same representation of these levels.
Yeah, but it's, I mean, it would be nice to have that argument explicit. Like, show how it's done.
It might be possible. Let me take a subgroup of SU2 and somehow find a connection with V1.
Right. The representation of the SU2 and the representation of the subgroup.
Yeah. Yes, somehow I thought about this, but I didn't. Very well.
Or at least some isomorphism between the SU2 and U1 representation.
Isomorphism, probably not. Homomorphism.
Well, for certainly, subgroup, which is isomorphic to V1. No, sorry,
Sure.
it's out.
How does that
So,
gets represented if you take different representation of SU2? So if you take spin one, how is that subgroup represented?
yeah, I mean, consider these as subgroups of SU2, and then it might be justified to use this inner product. Well. So. Yeah, so normalizability, it would normalizability, but this doesn't solve all problems. Now, this should be physical states where you consider expectation values and uncertainties. So we have the volume is M and K. K is the cross-section area, the quantum number of the cross area. M divided by K, so K bar is a length. Of cell. Well, that's within. So we have another edge, so some other vertices, and okay. The mean value 1/2 K plus K minus. Continue. Then there is expectation value of M divided times mean value. Well, this expectation value cannot be easily calculated. 1/the square root of K bar.
So can you say what you mean by this notation for the volume? Like square root of M comma N?
No. Nonsense.
Okay. Also in the definition. Yeah, for the L, those sense.
Yeah.
Okay, okay.
Now this is the sum over n, a and n squared might be, as you have seen, it might be complex. Square root of n divided by 2n plus 1 to n plus 1. What is converges? This goes like 1 over n, this 2, so we have 1 over n squared, and here the square root is get 1 over n to 3 halves, n to 3 halves converges. So find the physical expectation value is finite, but now take for delta L uncertainty, we need the expectation value of n squared, which contains, well, 1 over a is the expectation value of n. And take first the sum along the axis. So the n axis, sum of n, a, m, and 1. N is equal to 1 with the axis squared. N, this is m times 1, divided by 2m plus 1, 2 times 1 plus 1, goes for large m, like 1 over 6m. Unfortunately, we will divert this again. When we go here along, or then when we go along the diagonal direction, we have some tolerances here. M, N, A, M, that's just N is equal to M, A and M, square, N square, divided by 2M plus 1 square. And this goes like M 1 over 4 M squared. So here it would be from the problem arises on these coefficients and on these ones. Here, along the diagonal of m is equal to m, so when the wave factor is equal to 1, this would converge. Well, so for a first conclusion, the solution is the Killing condition. Is grading diversion longitudinal ones or extrapolations. The expectation value is finite for the calculations of the divergence. So, especially the coefficients large wave factor m over n fall off too slowly. No, again, we have the what we had was the U expectation value of the killing conditions plus or minus is exactly equal to 0. Delta U plus minus is equal to 0 without any fluctuation. And so we get divergent length fluctuations. Wow. Yeah, now we can try to renormal even with the SU2 inner product. It doesn't completely solve the problem. And so again, we can renormalize. Formulate this in a symmetric way with EX divided into two halves. Here's the square root and here's the square root. Now replacing EX, KX, square root of EX, and EX 1/2 plus some small number lambda, KX, EX 1/2 plus lambda, or EX 1/2 plus lambda, KX, EX 1/2 minus lambda. Well, this is symmetric. But the density weight not equal to 1 anymore. It is 1 plus 2 lambda. So this means for integrating it, one would need certain coordinates. One would have to fix coordinates. When we change coordinates, changes. Well, this now is not symmetric. But the density weight is equal to 1. So both have some unpleasant features. Well, let's take denote this again by 1 and this by 2. Now, for 1, let's say we have A and in this simplest case is now n 1/2 plus lambda for E equal to W equal to 0. This simplest case of all. So this would already converge. No. The coefficients fall off more rapidly, and then we can consider speed and length uncertainties. Well, now this is A and N. 1 and N. 1/2 plus lambda. And we can calculate M and N. This now some and one over no from 1 to infinity, and now we have m and 2 lambda. And then once this square just cancels here, and we have the 2 and plus 1, 2 and plus 1. And for large, for large and n, yes, 1 over 4, 1 to and 1 plus 2 lambda. And now we can estimate it by an integral. Way from to infinity, say from 1, you can choose anyway, we estimate the problematic symbolic region. And then we find that this n is of the order 1 over 4 and integrate m and integrate n. 1 over 17, 1 over 16, 1 over lambda squared. Quite simple integrals. So this is an estimate. And expectation value, the square root, essential part of the next. It's quite the same way, it comes out as 1 over 4 lambda plus 1/2 squared. And then we can calculate delta L in lowest order in lambda, and lambda is a small number, is 1 over the square root of and what value of A and 1 over 4 lambda. So let's make this a little bit more quickly. And then we need the uncertainties of speed of the killing condition. We have mu plus or minus psi is equal to 0. The expectation value of u plus or minus no, is equal to 0 because when we have such a state, graphically here, and here, and this is psi, u psi is exactly non-zero at the other places. So when we take u psi and take the inner product with psi, you get 0. Those are different, non-zero different places. So the expectation value is equal to 0 also. And U plus square is U plus psi, the norm square. Also can calculate it, which this state act with U plus or with U minus on it, and then take the square, and this leads, again, we can estimate the point. Integral kx dx plus ky dy square is then 4 lambda square divided by 1 plus 4 lambda plus 4 lambda square. And this is approximately 4 lambda square for small lambda. What this means, as this is equal to 0, this means that delta U plus is the square root of it, 2 lambda. Now we can compare delta L times delta U plus is 4, 2, and we have 4.5, 1 over the average value of k. And the lambdas in first order for small lambda cancel. So we have this relation. A constant for constant case. And yeah. And this was for this choice. I didn't yet calculate this. I just had the idea maybe 2 days ago that we could also do this. But I don't really know what happens now. It seems to be like the first of the constant. The product of the uncertainties gives a constant, and then n, yeah, it's a last alternative. We found out that when we calculate the sum in this direction, just with the SU inner product, the uncertainty would be finite for each sum in this direction. This. What really matters are that here is the coefficients here are too large. They don't fall sufficiently quickly, so one could try a renormalization which lets here these coefficients untouched and suppresses the coefficients of diagonal. The more removed from diagonal, the more it should be suppressed. And this is also the reason why I said we might not completely disregard this case of an only partial common solution, because anyway, if we suppress coefficients here going more and more, then anyway, that's as soon as something is modified, especially if it's modified here in this and this direction, it's not a solution of the killing condition anymore. So if it's an approximate solution here and here less, so this wouldn't be so fatal. We also could consider this. So large wave factors. And I can again just mention some ad hoc possibility. We by factor e to minus lambda, something n minus n, or e minus omega n minus n square. Just when going away, we could suppress it, and this leads to, if we consider this once more in the classical conditions here, the uppermost line, kx ex plus ky ey. This will come out if we multiply this by e to lambda, ex plus ey, is equal to minus e prime. Then this would lead to something like that. And to the meaning, this is the time derivative. This is the factor greater than 1 minus. And this is the z derivative. We can subtract it to the other side, so we can take the time derivative kx ex plus ky ey is equal to minus e prime e to minus lambda ex minus y. So now the time derivative is less, smaller, but this is equal, and we get a factor 1, then the absolute value is smaller than the absolute value of e prime. So the time derivative would be smaller than the z derivative with the factor depending on the wave factor. This would also mean that large coefficients, solutions with large wave factor are slowed down. If this all makes sense, it might be we find a dispersion relation that when we have very large wave factors, large gravitational waves, they might be slowed down. The time derivative might be less than the z derivative.
There are some questions. There are some questions.
So you did not actually calculate the dispersion relation, or can you get it from this?
When we go through this formalism for machinery, we come to such a factor, which suppresses the functions.
Yeah.
Also, the farther away coefficient is from the diagonal, the more the farther away is also from being solution of given condition. It could be that it could mean that such large wave factors, the larger the wave factor, the less it satisfies that time derivative is just equal to the z derivative. at the speed departs from c.
Then now, the question. Okay, from.
Well, then, thank you for patience. 53.
Oh, maybe I have to lunch now.